So welcome back to the second half of the sixth class, where we're talking about probabilistic modeling. Right. So in the first half, we discussed, how if we have a bunch of numbers, basically a data set, and so we want to summarize it, then think back of the world before computer graphic or even before a fax machine. If you want to summarize a whole bunch of numbers with just its representative summary, then some representation of where the central tendency, in other words, the mean of that set of number is, would be a good start, right? So if you had 100 numbers and you want to summarize them, maybe the first summary is the mean. Just take an average, add them all up and divide by the total number. And if you want to sort of like give an idea of how spread out around the mean, then you can give number like standard deviation. And then you talk about third moment, fourth moment, and I show you how that corresponds intuitively to some picture in your head. Okay, and I drew some picture, like a normal curve, this kind of like positively skewed curve, but those are hand drawn, right? Okay, well, probability model is about drawing those lines mathematically, okay? And then do it in such way that not only is it drawn mathematically, the parameter of those mathematical function is chosen so that the line you draw best fit the sample that you have on your hand. Okay. So the concept is, well, I guess nowadays we might as well start with the concept of histogram. Let's say you do a histogram of your data and you get something like this. Okay, something like this. And you know that this number cannot be negative. And it can be any continuous number. And that is sort of like the histogram of your data. The idea here is to look up among the family of function that mathematicians have come up with over the year, and you decide, hey, I'm going to look over a function that's defined over 0 to plus infinity. Okay. And let's say among those, there are 50 of them I can choose from. I'm going to choose the one that has this shape, and I'm going to use a parameter so that it kind of fits best. Okay. So that's it, right? Now, analogous to the example I gave in the very beginning of class, now instead of sending your factory all the individual measurement, all the individual numbers, instead of sending the facts of the picture of the histogram, now you can say, hey, that data that I have in my hand consists of 1,000 numbers, can be described, for example, using gamma distribution with parameter 1.2 and 3.4. Okay, so it's a little bit longer than one word, but certainly not the whole 1,000 number. Okay, so just like before, right? Before I said, I have a 100 number, I want to send you a summary. I can't tell you what it is. I'll tell you what the average is. So that's the mean. I'll tell you what standard deviation is. I'll tell you what the kurtosis and the skewness is. And you picture in your head what sort of data I have. Okay. Now, what I do is I put all those data in my computer. I run a little mathematical program called find distribution. And it found the distribution named gamma with parameter 1.2 and 3.4. So now it's not only just a summary, it's actually a model. My understanding is that in the future, when I run into this kind of situation, that's going to be the distribution. Okay? So now I can send a text message, say gamma, open bracket, 1.2, comma, 3.4, close bracket, end of story. Okay, that's how it would be like now that we have the language of mathematics. Okay, that's what we mean by that's what I'm going to do right now. Okay, so with the language of mathematics, it's even more precise. It's not about where the center is. Is it wide apart or is it positively skewed, negatively? It's about exactly what shape. Okay, with the language of mathematics. Now the tricky, of course, how to come up with that. Okay, so what happened is number one, this is a function. That the purple line you see is a function, and it depends on the parameter. Some parameter give it a little bit more push to the right, some push to the left, blah, blah, blah. So you can adjust the shape. The general shape is the name of the function. Okay. Another shape could be something like this. Okay. I don't know. Okay. So the general shape is the name of the function, but the parameter that you use by fitting the data is what gives it the particular shape, right? So it's a different, so this is, let's say this is a gamma, but this is a good gamma. This is a bad gamma, right? So just because you got the right name, it doesn't mean you have the right parameter. So you have to do two things. One, select the right family or the right name or the right brand of distribution function to fit the data. Chose the right one, but I didn't have to choose the right parameter to fit it. Two-step, okay? So that's the name of the game. So what has to happen is two things, okay? One thing is mathematicians have to, over the years, accumulate diverse shapes. It's like your job is to draw a picture with basic geometry, okay? And that geometry means you can draw with a triangle, a hexagon, and every one of them has a parameter. But you wouldn't be able to do it if nobody invented hexagon, right? So mathematicians have to invent those functions for you first, for you to select from. It's like, again, you can order noodles. You can say this noodle is hot or not hot or salty, but somebody has to invent noodle. Okay, then somebody has to invent spaghetti. Then you can specify the spaghetti parameter. Okay, but unless somebody invented spaghetti, you can't specify spaghetti parameter. It's that sort of thing. Okay, so let's see how mathematicians came up with recipes. Well, first of all, they have to agree on something, convention. Before the break, we already saw that mathematics is always about numbers. Where can number be and what function can you make on top of that, right? And we talk about 5 cases of where a number can be. And the reason they come up with those 5 cases is because it corresponds nicely to practical usage where we need to talk about nominal, ordinal, interval, and ratio scale. Okay? So let's agree on this. There are 2 kinds of distribution probability model. Okay, one of them would have a discrete. The other one is continuous. Think of it like this. Okay, and this is continuous. Okay, and we saw that separation, right? The discrete is very good for nominal and ordinal scale, and continuous is good for interval and ratio scale, right? Okay, so let's just, instead of having 5 groups, I'm just gonna say 2 groups for now. Okay, so I could do something like this. Discrete, continuous, finite, countable, bounded, semi-bounded, then unbounded. Okay, but right now I'm just gonna talk about 2 major groups. Can we do that? So the first one, so I'm going to start thinking of probability shape, right? Now, first of all, probability, let's agree this, okay? Let's agree that probability cannot be negative, okay? You can have zero probability, you know. I asked this girl out, I have zero probability she would say yes, but I don't have a negative probability, right? And the worst canvas is zero probability. I'm taking this extremely difficult exam. I have zero probability of passing it. I don't have a negative problem. So first of all, probability cannot be negative. Yeah, that makes sense. That makes sense. So that's the agreement. So that's called axiom number one. Maybe number two, I'm not quite sure, but yeah, look at the book. So definitely probability of anything whatsoever cannot be negative. Okay. Second, probability of all possible cases must add up to 1. In other words, 100%. So this is where you can't say something like, I am 110% sure, or put in 110% effort. Doesn't work that way, right? Okay. So probability of anything at all cannot be negative. Probability of all things, all possibility must be 1, because there's only one reality. Then it's about, proportioning that pie. So probability of any number 1, 2, 3, 4, 5, 6 has to be non-negative. Probability of 1 or 2 or 3 or 4 or 5 or 6 together, add them up together, must be equal to 1. Okay? So that's number 2. Probability of everything is 1. And the third one is about, well, if the probability of 2 things are disjointed, in other words, the coin, the dice can only land 2 or 3. It cannot land both, right? So you take probability of 2 or 3. It's the same thing as take the probability of 2, add to probability of 3. Okay. So if I don't have a coin, I want to play head and tail, but I have a dice instead. What I can do is this, guy. I can do this. I can say, hey, tell you what, if it's an odd number, I say it's 1. If it's even number, I say it's 0. In which case, what's the probability of 1? Well, that's a probability of 1 plus probability of 3 plus probability of 5, which is 1/6 plus 1/6 plus 1/6. So you get 3/6, so it's 1/2. Probability of disjoint event, okay? The probability of the union of the disjoint event is the sum of the individual probability. That's it. That's the rule of the game. Does that make sense? Now, let's translate it to the shape of the function. First of all, okay, so this is the value that's random, right? Now, look at my hand. I'm writing x here. I'm writing x here. Now, for a continuous case, okay, watch my hand. I'm going to write probability using f. For a discrete case, I'm going to write probability using p, little x, okay? Now, when I have discrete case, what happened? What is the second axiom? Probability of everything has to be equal to 1, right? So that means sum of I, p, xi has to be equal to 1. Would you agree? Right? 1/6 plus 1/6 plus 1/6 plus 1/6. Okay. So if I don't have a finite, then definitely I can have infinite possibility, but the probability has to die down to 0. Otherwise, you can't, it would blow up, right? Right? Okay. So that's what it means. So this one here is very important. Now, On the other hand, for continuous case, now I'm not going to distinguish between bounded, semi-bounded, okay? I'm just going to use unbounded as an example, okay? Might as well look at this guy, guys. This guy here. The analog of summing all the stick equal to 1 is integral, the area. So the area fx dx from say minus infinity to infinity must be equal to 1. That's it. So that's the difference between discrete mathematics and continuous mathematics. By the way, for those of you who are interested in finance, you can see me for project and whatnot. But in finance, it's very clear in quantitative finance, there are two types of reality: continuous reality and discrete reality. In reality, all finance is discrete, but mathematics is easier to do in continuous. So sometimes you would say it's approximately continuous. Okay. So for example, I'll give you an example. Is value of a stock, is that continuous or discrete? Anybody? Well, when you model it, it's continuous. Okay. But is it really continuous? Can you go by 1.2347894? No, it's actually finite, right? So like maybe fourth decimal or something. Okay. But fourth decimal, that's still finite, right? So it's actually discrete, but it's terrible to work with discrete mathematics in finance. So in finance, it's one of those things in life where deep down, everything is discrete, right? Because you go down to the cent and then you have to round it up somehow. Nobody talks to you otherwise. It's fundamentally discrete, but virtually 99% of financial models is done with discrete variable, with continuous variable. Okay, so that's real life. Okay, so let's agree that there are two types, right? There's discrete distribution and continuous distribution. Now, in theory, there could be mixed, where sometimes over this value is discrete, over this value is continuous. It will be something like I can give you a fail or a passing grade, but the passing grade is a continuous number, whereas fail is discrete or something like that. Or withdrawal is a discrete. So yeah, that's very rare case. So most of the time you either deal with one or the other. Okay, you don't mix them. Fine. So you agree this shape would be okay, right? Now, if I were to draw this line negative, would you accept that? No, you would not, right? Likewise, the bottom, if it dips below 0, would you allow that? No, you wouldn't allow that, right? So that's it. So let's imagine that this is the rule of the game. It's like a food safety standard. If you're gonna invent a food, it has to be cooked, it has to be edible, it has to be clean. If you're gonna make up a probability distribution, tell me, what kind is it? Discrete or continuous? If it's discrete, all the height has to add up to 1. If it's continuous, the integration or the area under curve has to be 1. That's it. Now, imagine you did this 300 years ago. You set out the rule, okay? And then you wait a while, and then you let mathematicians invent all kinds of functions. You can imagine that it's going to be very big, right? It's like menu. In fact, that's reality. You today, right now, can come up with a brand new distribution function and name it after yourself. Okay? As long as it satisfies those criteria and nobody's invented before you, you can name it after your family or your pet dog or whatever. Okay? So I can create this really weird looking, I don't know. Yeah, and call it my, I can do that. You can do that. Yeah. Nobody does. Why? And this has to do with usefulness. And this is where practical or applied mathematics comes in. Applied mathematics or practical science and mathematics doesn't mean no mathematics or easy mathematics. It just means that it's the mathematics that represents reality. Okay? Applied math, that's what it means. Okay? Applied math means mathematics that can be applied to things in real life. It doesn't mean it's easy mathematics. A lot of people say, give me some applied math. And they think it's easier math. No, it's not. It can be very complicated. The point is that it represents something that you see in real life. That's why it's useful. That's why it's applied. So this can be, easy, but it's not useful, so nobody follow it. Okay, so let's think about what could be useful. Okay, ask yourself, what would make, let's say you have a room full of mathematicians. Each one of them has come up with 5 different functions. Okay, and let's say you have to be a judge. Okay, I'm going to buy this function. This function is not good. This function. How would function gain popularity or gain utility, usefulness? How? Well, you can think of it 2 ways. Remember, I told you about the fitting exercise. You put the histogram, and you select a function, and you fit it, right? Well, imagine that you have 5 million histograms. And then you look through all the histogram and you say, what kind of function best fit? Okay. And let's say 30% of that function can be, 30% of that histogram can be fit with a gamma distribution. Gamma distribution would be something that you would invest in, right? Right? So basically the usefulness is how often or how well it fit data. That's it. That's one concept. On the other hand, you can think of it the opposite end. You can think of, randomness. Randomness. How does randomness take place? Well, you can have like head, tail. That's a randomness. Or you can say, well, what if I have a head, tail, coin toss, but I have 10 of them? So maybe creating a multiple coin toss is a useful function, right? Because in many situations in life, it's a sequence of yes and no. Okay. Would you think that creating a function that represents probability of yes and no in sequence of 10 or whatever would be useful? You might think it would be. You might think it would be, right? For example, you are a door-to-door salesman. You go to one house, you make a sale, you don't make a sale, 1, 0. You walk across the street, you make another sale pitch, you make a sale, you don't make a sale, that's another 1, 0. You do this for 10 homes. What's the worst that can happen? 0. What's the best that can happen? 10. Aha. What kind of distribution function would you, which kind, which family? It's going to be finite, right? Because either you make no sales or 1 house or 2 house, 3, 4, 5, 6, 7, 8, 9, 10. Because you visited 10 houses that day, right? You can't make 100 sales. So you can make 0 sale, 1 sale, all the way up to 10 sales. Hey, that makes sense. So if I make 10 house calls, each house has the same probability of buying, this distribution would make sense, right? So there are phenomenological, in other words, the phenomenon itself suggests why certain probability creation is useful. Okay. So let's focus on that for a minute. Let's say let's say I do this, okay? And you do 10 sales. What's the probability? Okay, let's do this together once, guys. Let's make it 5 houses, okay? So I don't run out of room, okay? Guys, watch my hand. 0, 1, 2, 3, 4, 5. Okay. Now, making sales is difficult, so it's not going to be 50-50. Maybe it's 110. Yeah, probability of success. So I'm going to give you a little p. Okay. This little p, unlike the other p, that's a function. This p is a value. This is my parameter. P for parameter. Point, let's say 1, 1. Okay. 1, 1. Okay. Now, let's construct probability. Now, guys, don't look at your computer at all. For the next 5 minutes, just look at my hand. Okay, this is my setup. This is my setup. I have this P is equal to 0.1. Okay, so I have a 1 in 10 chance of selling. Okay, my question is, what's the probability of 0 for the whole day? For the whole day? Okay, think again. I thought it's like, think of a coin toss. I have probability of making no sales, so that's 0.9, right? The point is that's just one house. So I have to go to the next house and I have another 0.9 probability. So, but that 0.9 probability only happened after the first 0.9, right? So it is multiplied together, right? I have probability of 0.9 that I'm not going to sell the first house. Then I walk to the next house. I have another probability of 0.9. So 0 is easy to calculate. That's my P, right? P is sale, right? 1 minus P is 0.9, right? To the 5. Okay, so 0.9 times 0.9 times 0.9 times 0.9. Okay, that's pretty high. Okay, that's pretty high. Okay. What's the probability I sell all the houses? Well, it's 0.1 times 0.1 times 0.1 times 0.1. So it's going to be very tiny. Okay. Now, here's the tricky part. What's the probability I'm going to sell 4 houses? Well, write it out. I'm going to sell the first house, second house, third house, fourth house, and then 5th house I don't sell. Does that make sense? Right? So it's P to the 4, 1 minus P to the 1. Is that it? Think it. That's probability of me selling 4 houses and not the last house. What about I sell the last 4 houses, but not the first house? So there is this thing. There's this thing, this thing, this thing, this thing, right? I have to add it, right? Because I have to, these are disjoint event, right? Someday I sell the first 4. Someday I sell the last 4. You can't, can't be the same day. Is that done? No. There's 3 more possibility. Cell, no cell, 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 cell. Cell, cell, no cell, cell, cell. Cell, 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 no cell, cell. There are 5 possibilities, right? So after all that, I'm gonna probably get something like this. Okay. Now, I truly apologize. I can do this live in Mathematica, but my license came out and for some reason, I have to enter the activation key again or whatever. Okay. Sorry. Yeah, you're too, right? Come after class together. Yeah. So anyway, the point is, the end story is okay. Probability. Now I'm going to write it as a function. Okay. Of x. Okay. Is equal to p to the x. So x could be 1, 2, 3, 4, 5. 1 minus p to the number of times minus x, right? So let's say n is a number of houses. P is the probability of sales on each house. So that will be n minus p minus x. Okay. Okay. Now, this doesn't account for special term here that count multiples. Okay. That counts multiple. Okay. And that multiple is given by formula called n choose x. Don't worry about it. Okay. The point is, you can see why there's a logical construction to this. So, when would you use this? You would use this because, well, you happen to see up to n and you want to fit. Or you would want to use this because you knew the randomness happened in this way. The randomness is the number of sales in a fixed number of attempts, given that each attempt has the same probability of success. Now, if it has different probability of success, would not have the same p, right? That'd be more than that, right? So in this case, it's a simple case, but believe you me, this is one of those superstar of probability distribution because it happens all the time. Even though the probability of making a sale from house to house can vary a little bit, in practice, you can treat it as being the same. So if you have total number of success, given number of trial, finite number of trial, given n trial, each trial has the same probability p of a success, and you add how much total success you've got. Okay. Now, if I make p equal to 1/2 and n equal to number of coin toss, this is nothing more than probability of total number of heads. Right? P is the number of heads, right? I make a coin toss 10 times. What's the probability of tail? Well, it's 1 minus P, 1 minus P, 1 minus 10 of them. What's the probability of all heads? P, 10 of them. What's the probability of 9 heads and all, 1 tail? It's P to the 9, 1 minus P to the 1. And how many possibility? 9. Oh, 10. 10. Okay? Right? So that's the mathematics. So think of it two ways. The probability function are useful popular because A, in real life, it's good fit. Or B, actually it corresponds to the actual process of that randomness. And this one is so useful. Why? Because so many things have that, especially after Industrial Revolution. When you have Industrial Revolution, you are making a lot of stuff. So if you think about N as a batch of 1,000, right? N is 1,000. Every day, your factory makes 1,000 pair of shoes. Each shoe has probability P of being defective, right? What's the probability of no defective? 1 minus P to the 1,000. Now, the extreme is easy. It's the combination in the middle. That's a little bit tricky, right? Okay? Because if you have 3 defective, you can have first 3 defective or last 3 defective or any 3 in there defective. They each contribute same probability. So you have multiple copies of that, right? In fact, numerically, you would have, I'll give you, probability of 3 defective pair of shoes given 1,000 is equal to, okay, 1 minus P, right? To the power of P is defective. In this case, success is bad, okay? P is defective. So 1 minus P to the 997 times P to the 3. Now you have to do this. How many ways can you pick 10 out of 3? And this turned out to be equal to 1,000 times 999 times 998 divided by 3 to 1. So this is a big number. Okay, that's just how many ways, right? How many order can you have 3 defective out of 1,000? If it's just 1, then you can just have 1,000 of them. Okay. So this here is so useful. This is also superstar. Okay. This be like Meryl Streep of probability distribution or something. Okay. Because this is so often the case, okay. Now I'm gonna write this, and I want you to look at my hand, see if you notice something different I did. Take the picture of this, guys, because it's supposed to confuse the heck out of you. I'm not being mean. This was done to me, so I have to do it to you. Okay. First of all, this is a little p. This is PR. This is little x. This is big X. This is little x. This is big X, little x, n, little p. There's also little p. And this is also little p, but they're not the same thing. Oh my God. Is life tough for you now? Okay. If you can get this, you can go home. Okay, because this is the most tricky concept. There is, everything else is mechanical. Okay. And trust me, Most of the time you take probability statistic, you skip over this and this is not understood. First of all, okay. First of all, when I say this, I'm going to say, let X be a random variable. Okay, I'm going to write that word down. This is called random variable. The big X. The big X is called random variable. Okay, go home today and read the book. It's going to say it's not random, it's not a variable. But I'm going to tell you. Okay, read it again. Okay. First of all, it's not a variable. A variable means something happens and sometimes this happened, maybe that happened, this happened, maybe that happened. However, in this case, if I land a coin and it's head, I have to call it 1. That's my definition. Can I change that definition mid-sentence? No. Same with factory defect. If I say P is probability of 1 defect, that means defect is equal to value 1. What it means is that you're standing at the end of the factory, you look at it, it's okay, it's okay, it's okay. If it's okay, you say 0, 0, 0, 0, 0, 1. You call out 1 whenever you see defect. My question is, are you doing this randomly? Are you doing this randomly? No. You are not random. Production process is random. Production process may give you perfect shoe, defective shoes. But you, the call out function is fixed. Every time I see good shoes, I say 0. Every time I see bad shoes, I see it 1. So it's not random. And it's not even a variable. It's a function, guys. My input is reality. Think of convolutional neural network. When there's a cat, 1. Right? What's random is whether or not a cat will walk in front of the visual pattern recognition. But your iPhone scan this and it's a cat. That function is fixed. Yeah, if it's perfectly, error-free. In this case, it is error-free. Every time I see defective pair of shoes, I say 1. Every time I see good shoes, I say 0. And because I say it, I am a function. So it's not a variable. And the way I call out is not random. What's random is nature. Okay? So it's not random, it's not variable, it's X. But it's called random variable. Why? Because it looks like a variable and has to do with randomness. By definition, a random variable, and this is not changed, this is not format, universally uses big letter, capital letter. Okay, this is one of those times where mathematicians are very strict about notation. The value that it takes on is the little x. That's called random variant. This thing here is random variant. It's the value, the actual value that you plot. Okay? So that's the one that has to be countable, finite, infinite, or whatever. Okay? The value. And what's the value here? Well, in my case, it has to be between what? In this case, 0, 1, n. Because of this model is a finite probability model, right? Now, this is the random variate. This is a random, sorry, this is a random variate. This is a random variable. This is the name short for binomial. Binomial. Let me say that again. Binomial. Why is it called binomial? Because it's constructed from two terms, 1 or 0. Okay, so they call it binomial. It's a binomial distribution with two parameters, n and p. The n parameter tells you what's the maximum value, how many try it gets, how many houses you visit, how many shoes you produce. P is a probability of 1 or probability of bingo, that's it. You make a sale, or 1, bad shoes. Okay, so P is a probability of 1 for each trial. Okay, so that becomes a number P, whereas P here, okay, guys, I'm sorry, but this is life. This here is the probability mass function. It's what you plot. So this is X, this is P of X. And this P is called probability mass function, PMF. Probability mass function. Okay, PMF. Why is it called probability mass function? Because it's a function that gives a probability mass. Okay, so it gives a little bit of mass here. Mass, think of mass as lump. There's a lump here, there's a lump there, there's a lump here, lump here, lump here, from 0 to n. So it's a probability mass function. Okay. So, and what is this PR here? And what is equality here? This PR stands for probability that X, random variable X, takes on value or variate. Okay. Okay. Are you as exhausted as I am? I am sorry. This is not, I did not invent this. Okay. This is how the whole thing is written. Okay. Probability now. And this squiggly line, oops. This squiggly line is a shorthand for a sentence in English called random variable X is distributed according to, do I need to write that down? Okay. Random variable X is distributed according to binomial distribution with parameter n and p. And if you tell me what n is, for example, n is equal to 10, p is, for example, p is 7%, I can draw you this probability of X. Okay, so, okay, the table at the beginning of the lecture where I created the sample data, when you see this squiggly line, that's where I came from. Except instead of binomial, the one I think you saw would be normal and gamma or something. I'm not quite sure. Beta maybe. Okay. So this is just one variety, but I'm giving you the, Meryl Streep already. So this, if you know this, you can make a living almost. Okay. Now, this is the queen of all probability distribution in a discrete world. Okay. Let me quickly, because I think I ran a little bit over time. Let me quickly write something like this. Write something like this for a continuous world. Okay, you guys got this, right? Take a picture of this. Okay. Let X random variable X be distributed according to normal distribution function with parameter mu and sigma. Okay. And this corresponds to continuous case. This is the Robert De Niro of distribution function. For continuous case, you see this all the time. Because it's continuous, I'm going to write f of x. Okay. And again, you may have come to this class thinking this is easy review of high school. This is not. Okay. Such that, okay, what? This is mu. This here is sigma. Yeah, doesn't have to be, okay, this is here. When I say sigma, what I mean is this is got about 68%. Okay. About. Okay. Now the function for this, okay, I'm not going to be mean, but I will be mean. F of x is equal to 1 over something e to the minus 1/2 x minus mu divided by sigma squared. Now, next week, my Mathematica should be fixed. You will see why this works. The point is, this equation is a mathematical equation. It has two parameters, mu and sigma. So this is the name of that. So when I write to Mathematica, I want normal distribution. In Mathematica, I don't use just n because n stands for numerical. I write normal distribution, open bracket, A and B. A is this, B and that. Now you will see, open your book to the first table under the chapter heading. I would write normal, open bracket, 0 and 1, or normal, open bracket, close bracket. Because by default, if you don't specify, the standard way is to say, hey, let's set this equal to 0, and let's set equal this to 1. Okay? And everything else just stretches from there. So basically, if you know how to draw this picture, okay? It's like I asked you to draw a picture for a given sigma and mu. You know what you do? You draw the same picture, but you label it differently. Okay, so you draw this thing first, and the middle, you say, yeah, that's where the mu is. Okay, I asked you, draw another one, make mu 5,000. Okay, that's 5,000. Draw another one, make mu 10. That's 10. So you don't have to say change the shape. The shape will be like this. Mu plus minus sigma will give you about 68%, which is a good majority. And that's where you get this X bar plus minus standard deviation come from. Okay, so if I tell, okay, back to the very first statement or first example in the class. I walk in here, 100 people, I take the height. The first number I report is the mean. The second number I report is standard deviation. That's a real number, guys, from real data. For that data, the best function to use is this guy. And the best number to use for mu is mean. The best number to use for sigma is standard deviation. So it's a lot more information, right? Because now it's more precise. I don't just give mean equal to 1.75, standard deviation equal to 0.1. I say that it's actually normally distributed or distributed according to normal distribution. A shorter way of saying it is the data is normally distributed with mean 1.7, standard deviation 0.1. And with that, I can use my own Mathematica and draw this thing. I can then tell you how many people. Now, once I have this, it becomes a model of future population. Now it's not this 100 guy, it's anybody. Okay, maybe anybody in your age group. Okay, so I can, if I make the shirt between this size and that size, I can cover 68%. If I want to cover 98%, yeah, I have to make it more. The point is, now you know exactly what, if you say, I want to make S cover the between S and L, short, small, medium, and large. Between small and large, I want to cover 68% of the population. Now you know where that S is. That S is mean minus standard deviation. You know what long is? Large is? Large is mean plus standard deviation. Okay? Now, if you want extra large, maybe mean plus 2 standard deviation. That's where things like plus minus sigma comes in. And that's the basis of how you discuss all the parameter of all the product specification. Virtually, you know, think of your clothes. Think of clothes as species. Okay? So this becomes this is a shorthand. I can write this just like I did in the first table underneath the title page. By writing normal mu sigma, I tell the computer everything need to know. So when I do this and I say, give me a function. Now, the last word is this thing is not concentrated at a point. So it's not like giving a probability mass. So they call it probability density function, PDF. So it's a PDF because it's not giving probability mass at a point, it's giving a concentration. So it's a density. So how do you find the probability? You have to do integration. Okay, my Mathematica will be fixed and I will show you how that is done. Okay, and this is it. This is the essence. Okay, now, so the difference between section 2 and section 3 is the following. Section 2 builds a whole bunch of this. Okay, it's like giving you a starting sample pack. You know, you're gonna be a professional chef. You know how, you should know how to fillet fish. You should know how to make sashimi. You should know how to make tom yum goong. Otherwise, nobody's gonna hire you. Likewise, if you're gonna do probability statistics, you have to know binomial distribution. You have to know normal distribution. You have to know gamma distribution. You have to know, you know, there are a few more. Okay, so that's section 2. Section 3 is about once you get the data, yeah, you have to estimate this. So that's called estimation. Conversely, if somebody claim that their mu is 1.2 and you look at the data and you say, oh, I'm going to call you bluff. Your mu is probably higher than that. Okay, that's statistical hypothesis testing. And that is basically bulk of statistics. And all this is 80%. The other 10 or 20% of traditional statistics is regression.